Good morning, students. Today we are discussing about new topic on continuation with E1 and E2 reaction, that is the rearrangement of carbocation in elimination reaction and also saytzeff rule. So we have already studied about E1 and E2 mechanism in the previous class. In E1 mechanism, there is two steps are involved. First one is the intermediate formation of carbocation. And this carbocation will undergo rearrangement to form an unexpected product. That rearrangement we are discussing in this topic. So this is the example. 3-methyl-2-butyl tosylate is an alkyl halide. This on elimination gives, it can give 2-methyl-2-butene, 3-methyl-1-butene and 2-methyl-1-butene. So these much products are possible from the single isomer. So sometimes the carbon skeleton itself also changed. And another example, 3,3-dimethyl-2-bromobutane on elimination gives 2,3-dimethyl-2-butene and also 2,3-dimethyl-1-butene. Two products are possible. So how we can assess which is the main product? The initially formed carbocation may undergo rearrangement by a 1,2 shift to form a more stable carbocation. That's why there is formation of two different products. So this is the mechanism showing that rearrangement. You can see in this first reaction, by the elimination of the tosyl group, a carbocation is formed on that second carbon, and that hydrogen is migrated to that carbon and positive charge is migrated to the carbon which is leaving the hydrogen. That is the rearrangement. That is, secondary carbocation was the first product. It is converted into tertiary carbocation because it is more stable than secondary. And the second reaction also, the bromine is eliminated and positive charge is associated in the carbon which contains bromine. And in the next third step, the alkyl group, methyl group is migrated to the carbon and the positive charge is migrated to the carbon which leaves the methyl group. That is, the secondary carbocation is converted into tertiary carbocation. And the third reaction also, the bromine is eliminated. Bromine is eliminated from that CH2Br and positive charge is associated is formed in the carbon, and in the second reaction the methyl group is migrated to the carbon and the positive charge is migrated to the carbon which leaves the methyl group. So here forms a tertiary carbocation. First it was primary, then it is converted into the tertiary, that is, which is more stable. So carbocation itself have a property to rearrange itself to form more stable carbocation. So in this new carbocation that loses the proton is preferably eliminated from the beta position to yield the unexpected alkene. So that's why the unexpected alkene is produced. So see this example, rearranged cation and chief product, and that was a minor product second one. And here also from the above slides the products of the reaction is discussed here. You can see the main product and secondary product. So what is the difference between this main product and secondary product? In this first reaction you can see the chief product. The double bond is attached to the carbon. The double bonded carbon is attached to a hydrogen, and here also methyl groups are there. In second product, that is the sub-product, the double bonded carbon is bonded to alkyl group in one side and other side two hydrogens are there. That means the more which contain more alkyl groups attached, that is the double bonded carbon which contains the more alkyl group attached on both sides are preferred over the other product. In the second and third example also you can find out what is the attachments in the double bonded carbons. In the second reaction, the chief products, you can see the double bonded carbons attached to are methyl groups. Two methyl groups are attached to the double bonded carbon. The secondary product of the second reaction, you can see the double bonded carbon is one carbon is attached to two hydrogens and one carbon is attached to the two alkyl groups. So one which has attached to more alkyl groups is more stable. That is the chief product. Third reaction also the same thing, you can check whether it is correct or not, you can check. So from that findings we are moving to next topic, saytzeff rule and its orientation and order of reactivity of alkyl halides. So the dehydrohalogenation of alkyl halides gives a mixture of isomeric alkenes. Which isomer will predominate depends upon the orientation of elimination. Here we are discussing about the orientation of that elimination, why it is preferred and why that is not preferred. So here one example, 2-bromobutane. You can see the beta hydrogens in colored and alpha carbon. Both the beta hydrogens can eliminate. And we can expect two products, that is 1-butene and 2-butene. Here 2-butene is preferred and it will get 80% and 1-butene in 20%. So this is one more example, bromopentane, and also third reaction. These two examples are there. You can see which is a preferred product. One which yield more percentage will be the preferred product. In the examples we can see that the disubstituted alkene is preferred over monosubstituted alkene and trisubstituted alkene is preferred over disubstituted alkene. So that is we are coming to the rule, saytzeff rule. According to saytzeff rule, it states that in dehydrohalogenation, the preferred product is the alkene that has the greater number of alkyl groups attached to the doubly bonded carbon atoms. So that is saytzeff rule. In dehydrohalogenation reaction, that is in elimination reaction, the preferred product is the alkene. Anyway, alkene is the product which is the preferred. That has greater number of alkyl groups attached to the both sides, doubly bonded carbon atoms. So we can analyze, we can conclude this concept through these steps, that is R2C, double bond CR2. R2 means there is two alkyl groups are there, and CR2 two alkyl groups. In the next one it is greater than R2C double bond CHR. CR2 means two alkyl groups are there. CHR means one hydrogen and one alkyl group. So that product is prepared as first product, and continuing the last is RCH double bond CH2. So I think we have already studied this same scheme with the stability of alkenes. Stability of alkenes also follows this same order, like isoformation of alkenes in dehydrohalogenation. Both are same. So alkene stability not only determines the orientation of dehydrogenation, but also is an important factor in determining the reactivity of an alkyl halide towards elimination. It also determines the reactivity of alkyl halide. For example, for reaction with the sodium methoxide in ethanol at 55 degree, even after we have allowed for the number of beta hydrogen, the relative rate per hydrogen increases as the alkene become more highly substituted. So is there some columns, some examples are there. One substrate and the product formed, then relative rates and relative rates per hydrogen. First one is bromoethane, then bromopropane, then secondary, and also next is tertiary. The first one general ethene, then primary, secondary, tertiary. So you can see the relative rates are increasing like 1 3.3, 9.4, 120, etc. And relative rates per hydrogen also increasing, that is 1, 5, 4.7 and 40. So from this we can conclude the reactivity of alkyl halides towards E2 reaction is tertiary greater than secondary greater than primary. So that is the conclusion. So here we are finishing this topic. So remaining topics of E1 and E2 reaction will continue in the next class. You have to write down these notes and also have to submit. Okay, thank you.